Today we are going to discuss coherent mode representation of optical fields. Coherent mode representation is quite important when it comes to studying the propagation of optical fields, the propagation of partially coherent fields, which is what these optical fields are in general. So coherent mode representation is basically of a partially coherent field is basically representing a partially coherent field as a sum of fully coherent fields or fully coherent modes. It is quite easy to kind of propagate and study the propagation of fully coherent modes as opposed to partially coherent modes. So once the field is represented, or once a partially coherent field is represented as a sum of a few or an infinite number of coherent modes, then what one does is just propagate these coherent modes independently, and then one then adds them all up in order to get the partially coherent field. So in some sense it's pretty much same as the coherent mode representation is pretty much same as the diagonalization of a matrix, and here as I will show a partially coherent field, we can visualize that as a matrix. In fact, we saw that for the polarization matrix was 2 by 2. And so similarly we'll see for the other partially coherent fields, for example the fields in time, space, angle, we'll see how to represent that, the correlation function, how to see that as matrix. Okay, so this is quite an important topic as far as propagation of partially coherent field is concerned. So but before we get into this, let's first look at what we did in lecture number 10. So in lecture number 10 we were studying the coherence in the polarization degree of freedom or coherence in the polarization basis, and for studying the coherence in the polarization basis, this is the generic interferometer we had. We start with the polarization in the two different directions. We introduce phase shifts epsilon 1, epsilon 2 in the two different directions, in the two different polarizations, and then we add the field by putting a polarizer and looking at what comes out of the polarizer, and the intensity of the polarizer has this expression. If you look at the visibility of this interference pattern as a function of or as optimized over delta, then this visibility is this omega x prime max minus mean over max plus mean, and this is equal to the degree of polarization coherence. We then looked at the visibility optimized over delta and theta. This thing we haven't looked, this kind of quantity we didn't discuss in the context of time, space and angle interference, but this we are doing here, and as we can see this cosine squared theta, this theta that we are going to optimize the visibility over, this cosine theta term was there also in the discussion of time, space and angle interference, but there we just wrote it as k1 squared, this was k2 square, and we didn't change it. This was a constant of a given interferometer. But suppose if we change this theta as well as this delta, then we saw that the visibility will have this kind of definition. Of course it's still of the form max minus min over max plus min, but this max is which is optimized over delta and theta, and so is the minimum. And then we calculated this quantity. Now in order to calculate this quantity, we first, so if we have an electric field in this polarization basis, then this electric field is written in terms of, in this vectorial manner, Ex in the x direction, Ey in the y direction. But this vector can also be represented in terms of a row matrix or even a column matrix. So when this is a completely coherent electric field, then this is the perfect representation, just the vector. But when we know that when this is not a perfectly coherent field, then this kind of representation is just symbolic. And the main thing that one has to look at is the correlation function. And what are the correlation function in the case of polarization? These are Ex star, Ey, ensemble average, Ey star, Ex, and then Ex star, Ex, Ey star, Ey. These are the four correlation functions we can have, and this can then be written in terms of a 2 by 2 matrix J. This we call the polarization matrix. So again, if a field is perfectly coherent, then this can be represented as a vector or a 2-element row matrix. But if the field is partially coherent, then we have to have the representation in terms of a 2 by 2 matrix. And the reason for this is that if the field is completely coherent, then this kind of quantity E star x Ey is simply the product of this quantity. If you know Ex, if you know Ey, then E star this ensemble average quantity is simply E star x Ey, which we can just find out by multiplying the complex conjugate of this with this. But when it's a partially coherent field, then we know that these E star xt EYT, that is not equal to E star xt EYT ensemble average. This is different, and that's why we have to study this separately. And that's why when it comes to the partially coherent field, one has to study the correlation function and not just the fields. So in the case of polarization, then this becomes a 2 by 2 matrix, and this we write as jxx, jxy, jyx, jyy. Now with jxx, as we saw, this is the intensity or the spectral density in the x direction of the x polarization. Jyy is the intensity or spectral density of the y polarization. And then we saw that the generic density matrix can be written as a sum of a completely polarized polarization matrix and a completely unpolarized polarization matrix, and the form of these matrices are like this. The polarized one is of the form BCDD star, and the unpolarized is of the form A11. That's just the identity matrix. And then we saw that this, for polarization, it has to be that the determinant of this one should be 0. That means BC minus DD star is equal to 0. Okay, so once we had this formulation, then we saw that the visibility can be written like this, which is 1 minus 4 determinant of J of this matrix divided by the trace of J square, and whole thing raised to the power half. This, then we saw that then we can, once we utilize this decomposition, we saw that this can be written as a trace of J polarized and J trace divided by trace of J, which is basically the intensity that is associated with the polarized part divided by the total intensity, and this we call as the degree of polarization, and it is a basis independent quantity, and it is equal to this visibility, which is also a basis independent quantity. So this is what we did. In the last class, we also saw that in terms of normalized polarization matrices, here J is just J polarized plus J unpolarized, but if we write this in terms of the matrices, the polarization matrices that are normalized, then we have this kind of representation. This is the same thing, J polarized plus J unpolarized, but now we are writing it as these polarization matrices that are normalizable, that is unit trace. So in that case, BC DD star can be written as all divided by P, and then this P comes out, and then this thing was 1 minus P, and this identity matrix. So if you write it in using these matrices, the polarized and unpolarized matrix that have unit trace, then the coefficient that comes out front of this polarized part, that is the degree of polarization or the visibility. So the degree of polarization has two interpretations. First is that it is the intensity associated with the polarized part divided by the total intensity, or in this kind of decomposition, it is the coefficient that comes out of that shows up in front of this, the polarized part, or basically the weightage of the polarized part. Okay. So now let's switch gears and let's get started with this coherent mode representation of optical fields. So essentially, this coherent mode representation is a way of representing a partially coherent field as a sum of fully coherent field. And as I said, the aim here is that propagating a fully coherent mode or fully coherent field is much more easier than propagating a partially coherent mode as far as solving the associated diffraction integrals are concerned. So, so for the finite dimensional basis, for example, we have just been discussing polarization basis. So we'll first look at this coherent mode representation, the finite dimensional basis of polarization. So in the polarization basis, coherent mode representation is equivalent to the diagonalization of the polarization matrix. We'll see how. Now, what are the conditions for the coherent mode representation of a polarized matrix? That means if we have a polarization matrix given, what are the conditions that one can actually find a coherent mode representation of that matrix? This can be said in other words as well, that what are the conditions for the diagonalization of J, that is a polarization matrix, with at least one positive eigenvalue. These two statements are pretty much equivalent. Now the conditions that has to be satisfied is that J has to be normalizable. That means the trace J, in other words, we can also say that trace J is basically equal to 1. If the trace J of this thing is equal to 1, that is the first condition. The second is J has to be a Hermitian matrix. That means J equal to J star. This condition is needed because we want this J, the matrix, to represent a physical system, a physical field. And for the field to be a physical field, the matrix has to be Hermitian. The third and the last condition is that J is a positive definite matrix. The positive definiteness condition is given like this, where A star, this ai, these are complex numbers, and this jij, these are the elements of the J matrix, that is jxx, jyy, jxy, jy. So that's why I goes from 1 to 2. So that is the condition for positive definiteness. Now what does it essentially means, at least for a Hermitian matrix, it essentially means that the eigenvalues are all positive, they are not negative. Now why do we need this? An intuitive way of seeing this is that when we write the polarization matrix, the eigenvalues of any matrix represents the in terms of, if we go back to our this representation, now this is how we represent the polarization matrix. Now suppose we diagonalize it, and in the diagonal form it will only have the diagonal entry and no off diagonal entries. Now the diagonal entry, for example, the diagonal entry here jxx, jyy represents the intensity of the x polarization or the spectral density of the x polarization, and jyy represents the spectral density in the y direction or of the y polarization. Now suppose we rotate this and it goes to some other basis x prime y prime so that it is diagonal, but the diagonal elements will still represent the intensity in the rotated basis. And now these intensities for a physical field can never be negative. So that's why this condition is needed, that the J has to be a positive definite matrix. That means its eigenvalues, they have to be positive. They cannot be, they can be also 0, but they cannot be negatives. That's why positive definite matrix. Okay, so now suppose there exists an eigenbasis x prime y prime in which J is diagonal. Suppose all these conditions are satisfied for a given matrix. We have a physical polarization matrix representing a physical partially coherent field. Now let's say there exists eigenbasis x prime y prime in which J is diagonal. Then this J, which is written in the xy basis as jxx, jxy, jyx, jyy, this we can write in the x prime y prime basis in which we know it is diagonal, like this. Just this diagonal entry is a1, a2, 0, 0. This is just a basis transformation, and just by the basis transformation, this 2 by 2 we can write it as this, and this of course can be written as a1, 1, 0, 0, 0, and then a2, 0, 0, 1, 0. So this is called the coherent mode representation of J. Now why coherent mode representation? Because this is a polarization matrix corresponding to a coherent mode. We see that the determinant of this matrix is 0, determinants of this matrix also 0, and the diagonal entries are greater than or equal to 0. So this is a matrix representing a completely polarized field or completely coherent field. Similarly, this represents completely coherent field. In fact, we can see this represents a field that is just x polarized, or rather x prime polarized, and this represents the field that is just y prime polarized. This mode has no component in the x prime direction, this mode has no component in the y prime direction. So this is a completely polarized field in the x prime direction, this is a completely polarized field in the y prime direction, and this matrix J, we are writing it as sum of these two matrices. Of course, these a1, a2, which are the eigenvalues, these are the proportion of x prime polarized light, and a2 is the proportion of the y prime polarized light. So that's the coherent mode representation in the polarization basis. So now of course the trace of this J is a1 plus a2, determinant of this J is just simply a1, a2. So if we want to write the degree of polarization, which is defined like this, we can just see that this determinant of J, if we put in a1, a2, so that's for a1, a2, for trace J it's a1 plus a2, so this quantity becomes a1 minus a2 divided by a1 plus a2. That's the visibility, and since this is a positive quantity, we have put the mod over here. So in terms of the eigenvalues of a matrix, we can write the degree of polarization as well. Okay. So this is the coherent mode representation in the finite dimensional basis, and here we have taken polarization. Now let's look at the coherent mode representation in the infinite dimensional basis, and we have studied 3 different infinite dimensional bases, which is time, space, and angle. So in the polarization basis, a partially coherent field is represented by the correlation function of the type jxx, e star x, ey. But in the continuous basis, we have studied 3, time, space, and angle. A partially coherent field is represented by the correlation function of the type w, rho 1, rho 2. So this is in space. If we are doing it in time, this will be W T1 T2, in angle it will become W theta 1 theta 2. So the point is that if it's a perfectly coherent field, then we represent it as an electric field, but if it's a partially coherent field, then we have to go to the correlation function, which is the product of the fields, and in which the one is complex conjugate, and that product we ensemble average. So it's the same quantity here. Okay, so now what are the conditions for the cross-spectral density function? I'm just writing it for the space. We could do the very similar thing for very similar thing for time and angle. So here we are writing it for space. So condition for this cross-spectral density to have a coherent mode representation are the following. It's very analogous to what we have in the case of polarization. The first one is that this cross-spectral density is square integrable. It's basically saying the field is finite, it's not an infinite field. So as long as this is square integrable, that means W rho 1 rho 2 integrate over rho 1 and rho 2. As long as that is less than infinity, this field can actually be in other words, this is the kind of essential requirement for the field to be physical. A physical field has to be square integrable, or the correlation function. The second condition is that the cross-spectral density function has to be Hermitian. Again, this is coming from the requirement that we are dealing with physical fields, and if it's a physical field, then of course the Hermiticity condition is always needed. And the last is that the W, the cross spectral density function, has to be positive definite, and this time is written in terms of an integral. So f star f rho 1 rho 2, this is replacing that a I a j we had in the case of finite dimensional, and this W rho 1 rho 2 and this integral, this has to be greater than 0. Again, this is essentially saying that the eigenvalues, or this is essentially saying no matter in which basis we represent a field, the intensities at every location rho 1 rho 2, every location rho, the intensity or the spectral density at every location rho has to be positive. It cannot be a negative value. The Hermiticity ensures that this value is real, but the positive definiteness condition ensures that this value is not only real, it has to be positive, it can't be negative. So these are the three conditions that we have. So here we can also see the Jx, it's easy to see the Jxx when we write this. So this is a matrix element of a matrix J. Similarly, W rho 1 rho 2, we can also see this as a matrix element of an infinite dimensional matrix. One direction is this infinite dimensional matrix characterized by these indices rho 1 and rho 2. So in that sense, we can also see this this coherent mode representation as essentially as the diagonalization. So if these conditions are satisfied, then the coherent mode representation of this rho is possible, and in that case we should be able to represent rho in this manner. Now what are psi star n and psi n? So these are the psi n, these are the eigen functions and the eigenvalue of the following integral equation. I mean, I won't go into solving this equation, but this is essentially the thing that we make this integral equation. We solve it for the eigenvalue psi n and the eigen function psi n and the eigenvalue alpha n, and then in terms of those eigenvalues and eigenfunction, this W then can be written as sum of alpha n psi star n rho 1 psi n rho 2. So there is no ensemble average over here. Now since psi star n is an eigenfunction, it's a fully coherent mode, we don't need angular average, and then we can write this as psi star n psi n, just some W n rho 1 rho 2. So this is the nth coherent mode. So this W rho 1 rho 2 is a fully coherent mode because we are writing it just as a product of psi star n psi n and not as an ensemble average. And if we have n such modes, on however is the number here, whatever is the number here, with those many modes we can represent this field. So this field, which is partially coherent, can be represented as a sum of fields that are completely coherent. And why they are completely coherent, that we can see that these W's are being represented by just a product and not the ensemble average. Okay, so for this continuous basis, it is not always true that one can represent this cross-spectral density function as a sum of finite number of the fully coherent modes. One can have, I mean, in some situation, it is possible that one needs infinite number of modes, and in which case this representation will essentially, we just have to replace this summation by an integral, and which is this g k w rho 1 rho 2 k d 2 k, and this the label n, which is we have over here, which is the discrete label, will be replaced by this continuous label k, which is what shows up here as well. So this is the coherent mode representation of the cross speckle density function. That means we write this partially coherent field in terms of, or as a sum of this w, we write this as a sum of the cross speckle density functions corresponding to the coherent modes, and these alpha n, these are the weightage. So essentially coherent mode representation is finding the diagonalization, and of course if there is no degeneracy in the eigenvalues, then this coherent mode representation is unique, just like diagonalization. If there is degeneracy in the eigenvalues, then one can have manifolds of coherent mode representation. Okay, and this is for the continuous basis. We can have, in fact it's not necessary that in the continuous basis we always have to have infinite number of modes. We can, even for the continuous basis, we can have finite number of modes. Okay, so now let's look at some examples. So the let me just comment that in general it is quite difficult to solve this equation. I mean, if for an arbitrary field, it is quite in general quite difficult to solve this equation in order to get the coherent modes. But here, as a few example, I just want to kind of point out the fields that we have already studied in these course of work. So just let's look at the field. This example, the first example is field with no correlation between different frequencies. This we saw in the context of studying the temporal coherence, and for such field the cross speckle density function is of this form, that w omega 1 omega 2 is just s of omega 1 delta omega 1 minus omega 2. This delta ensures that there is no correlation between different frequency component, because as long as omega 2 as soon as omega 2 is different than omega 1, this quantity is 0. So for such a cross speckle density function, we see that this cross correlation function, that is, which is a correlation function in time and is given by this we can then write as, just replace this w by s of omega delta omega 1 minus omega 2, and if we do that and then integrate it over omega 2, then we are left with s of omega 1 e to the minus I omega 1 t2 minus t1 d omega 1, and we can just get rid of omega 1 and write it as this. So just s of omega e to the I minus I omega t2 minus t1 d omega. This we had seen earlier as well, so I am just repeating here, but I am just looking at it from the perspective of coherent mode representation. So what we have is the cross correlation function, that means the correlation function in time, and this is in general a partially coherent field. It is just that this partially coherent field has no correlation between different frequency component, and for such a field this cross correlation function can be written in terms of in this form. And what we have done here, it just replaces e to the minus I omega t2 minus t1 by this gamma t1 t2 omega. So here we see that this the cross correlation function, that is the correlation function, we are writing that as a sum of, or rather as an integral over this gamma t1 t2 omega, which is completely coherent, because this gamma t1 t2 omega is essentially e to the minus I omega t2 minus t1, no ensemble averaging over here. So that's a completely coherent mode. So we are writing this partially coherent temporal correlation function or the cross correlation function as in terms of, or as an integral over the cross correlation functions that are completely coherent. So that's the coherent mode. This is just one example of the coherent modes, and this is when we know this about the field. Again, this is just one example, and here the gamma t1 t2 omega, which is e to the minus I omega t2 minus t1, these are the cross correlation function corresponding to the coherent mode. That means this is the field is e to the minus I omega t, and so for this monochromatic field the cross correlation function is essentially e to the minus I omega t2 minus t1, no ensemble averaging. So that's a coherent mode, and we are writing a general, not a general, but this particular cross correlation function as this in terms of this coherent mode representation. Let's look at another example. Again, I will just repeat myself here. So in the context of spatial correlation, we looked at fields with no correlation between different spatial frequencies. That is this the angular correlation function q1 q2 is of this form, sq1 delta q1 minus q2, And for this we can write this cross-spectral density function, which is between rho 1 rho 2 in this form. Well, that's the generalized Wiener-Khinchin theorem. So if for AQ1 Q2, if we substitute this form and integrate over Q2, we get this just by change of we just replace Q1 by Q, and we have this. So this W rho 1 rho 2 is S of Q, that is the spectral density at Q, and this quantity is the I Q dot rho 2 minus rho 1. Now this quantity we can write just as W rho 1 rho 2 Q, and that's how we can write this W rho 1 rho 2, which is the cross spectral density function of a partially coherent field, like this, where this is the cross spectral density function corresponding to fully coherent field, because there is no ensemble averaging here. So just W rho 1 rho 2. We are adding this Q here just for the labeling. So it is just e to the I Q dot rho 2 minus rho 1. So that's fully coherent, no ensemble averaging involved. So this is the W corresponding to a fully coherent mode. So that's the coherent mode representation of a field with no correlation between different spatial frequencies. So this is of course partially coherent, but we can write this field as a sum of, or rather integral over, these coherent modes, which are given like this, and this cross spectral density function is basically the one corresponding to the coherent mode is the I Q dot rho. So when we define this, we have the complex conjugate of this quantity and then product of this and ensemble average, but that ensemble average is equal to the product. So this is just the quantity. Okay, so similarly we can also look at the example for the angle degree of freedom, and in that case we had looked at the field that has no correlation between different OM modes. So for that we looked at the correlation in the OM basis as this. That's the two-dimensional Wiener-Khinchin theorem in angle OM. If we substitute this in here, this just becomes this, and writing in terms of just L becomes like that, and then so this W function in phi 1 and phi 2 will take this form. So this is a sum. This is a sum over these modes WL phi 1 phi 2. What is WL phi 1 phi 2? These are the e to the IL phi 2 minus phi 1. So here is no ensemble averagings, and this is the completely cross spectral density function corresponding to completely coherent mode. So that's a coherent mode representation of a field that has no correlation between different OAM modes. And WL phi 1 phi 2, the L is just the labeling, is the cross correlation function or the cross spectral density function corresponding to the coherent modes e to the IL phi. Okay, so these are the few examples we look at. Again, what we have seen is that in these cases we see that these are that's the coherent mode representation. In general, of course, finding the coherent mode representation of a general partially coherent field, that is a slightly involved mathematical problem, but here we had already looked at these fields. So here we do see how their coherent mode representation look like. Okay, so as far as now coherence is concerned, this is how much we will do in this course, the classical coherence, and these concepts, these coherence concepts that we have discussed so far until this lecture, we'll then see that this remains same as far as concept is concerned, even when we go to now that we go in the quantum domain. So from the next lecture we'll go into the quantum mechanical way of looking at interference. First we'll look at the interference involving one particle, one photon, then we look at interference involving two particles or two photons, but we'll see the structure of coherence remains exactly the same. So with that, let me stop here. Thank you.